Functions, relations, and their properties. Look at that picture on the board there. Is this something you've maybe somewhat familiar with, maybe not? You'll recognize it in a minute when we look at the different ways to view what a function is all about, okay? So these are some of the things we're going to cover. There's actually a few more, but we're going to talk about what is the Cartesian product, what's a function, a relation, domain, codomain, all a bunch of different terminology here, okay? Why do we care about functions, by the way? Why does it even matter? This chapter, chapter 2, is all about ways to represent and model data, right? A set itself is one way to model data. Using a Venn diagram is another way to model data. A function or a relation, those are two ways to model data. And if you've taken 2420, or you will be taking 2420, the algorithms and data structures class, that's what it's all about. Different ways to model data. That's what a data structure is, okay? All right, so let's get to the foundation here. What is the Cartesian product? Anybody familiar with that term? Yeah, it's a term that you'll hear in database world, which we're going to look at a database thing in a minute. But it is the product of multiplying two things by each other, two sets by each other, right? And it ends up with every combination you can have. So we'll look at an example, all right? So let's have a set called A, that's the values A, B, C. And we'll have a set called B, that's the values 1, 2, 3. The Cartesian product would be every ordered pair you could get of A comma B, right? So A1, A2, A3, so on and so forth, right? Like that. So this is just multiplying the two sets together, right? This is kind of like, yes, yeah, exactly that. Thank you, read my mind. Yeah, okay, so A cross B, the entire set there is every possible combination you can get of of combining A and B. And notice that it is an ordered pair, right? If I'm saying A times B, in other words, B times A would be different. B times A would be 1 comma A and 1 comma B and so forth. Make sense? Okay. This set, notice it is in brackets, it is a set, is a relation, okay? It's a relation from A to B, right? And any subset of the Cartesian product is called a relation from set A to B. Well, the Cartesian product is itself a subset of the Cartesian product, right? The subset can be the original set. So any subset of the Cartesian product, we call it a relation from A to B, all right? Make sense? This is a very common thing that you can see in database joins. You're not, you've taken database class or you do some database programming? Yeah. Who else has done some DB stuff? Yeah? Good. To the code. That's hilarious, man. All right, so let's take a look at the tables here. Let's do the customer table. So let's just select customer name from customer, okay? That's the customer name. One of the fields in this table, though, is the rep num, describe table. Oh, just not awake yet or something, I don't know. There we go. So one of the fields in this table is the rep num. So if I wanted to figure out who represented this customer here, right, I can say describe or select customer name and rep num from customer. And now I know that rep num 15 is representing Toys Galore, right? That makes sense. Okay, rep number 45. But who's rep number 45? Well, I could look in the rep table, right? Select star from rep. And rep number 45, oh, that's this person right here. So that person represents these guys, right? That's kind of a pain in the butt to do it, to look at it that way. So this is not a lecture on how to do a join, but I'm going to use a join right now. Don't worry if you don't know what that means. But what I'm going to do is everywhere it's 15, I want to replace it with Raphael. Or everywhere it's 30, I want to replace it with Grady, right? So that would look like this. Let's say select customer name, and then we'll just go with rep dot first name, just the first name, that's all. From customer, join rep on customer. Now if I run this, I get this. This is our Cartesian product. This is combining every customer name with every rep name. Every customer, right? That's Toys Galore 4 times for each rep. There's 4 reps. Okay, Brookings Direct with all 4 reps. That's a Cartesian product. And it is a valid query, and it is useful in some cases. In this case, it would be bad. This would be bad data. Okay, so again, if you're not a database person, or if you were and you just became confused because I had a brain cramp a second ago, sorry about that, then don't worry too much about that. My point in showing you this really is just to let you know this isn't some theoretical stuff that's just floating around the air. This is stuff that's in the real world, right? Sets and Cartesian products and subsets and all this kind of stuff. This is real world stuff, and when you get into database theory, you see it, and it's especially if you get into database design, it's all part of that. Okay, so what's a relation? This is what we're going to be talking about here. I just told you a minute ago that all relations are subsets of the Cartesian product, right? Well, it's just a set. A relation is just a set. It happens to be a set of ordered pairs, but it's just a set, okay? And you can have a relation from one set to another set. So again, we'll just say let set A equal ABC. We'll let set B equal 1, 2, 3. This is a subset of the Cartesian product. This is a relation. It's a valid relation. Now, and we'll look at some samples in a minute, but when you create a relation, there's always going to be some rule that says, hey, follow this rule, what will be the resulting relation? Okay, and we'll look at some examples of that, okay? Here's another subset. This is a subset of the Cartesian product. It's some relation called relation 2, and it has these components in it, right? So there was some rule that I applied to a relation from A to B, and I end up with relationship 2, or relation 2, okay? In the database world, we call tables relations. Right? That's another name that we use them for, okay? All right, so again, did we get this basic idea here that these are a relation from A to B? We can have any set of pairs, right? I could just have A1. That's a subset of the Cartesian product, right? Okay. Now, you can have a relation on itself, a relation from A to A, and we would call that a relation on A. Or if it was B to B, then we call it a relation on B or whatever. And we're going to see later a lot of different properties that can result from that, and that's one of the main things we're going to be talking about today for helping to represent data. All right? So let's take a look at a sample problem here. What are the ordered pairs in the less than or equal to relation which contains A comma B if A is less than B on the set 0, 1, 2, 3? Again, this is a set on itself, a relation on itself, right? And the set is 0, 1, 2, 3. And I'm saying I want to know every scenario where I'm going to have an ordered pair of A comma B, and where A will be less than B. Again, here's another way to word it. The ordered pair A comma B belongs to R, which is what we're calling the relation, if and only if both A and B belong to the set, and A is less than B. That's another way to say what I'm asking for. Make sense? Yep, 0, 1 would be in that set. Give me another one. Anybody? 1, 2. Another one?
0, 2.
0, 2. Good. You guys got the idea. Good. Okay, so the ordered pairs are, there they are. Every case, the number on the left is representing A, and the number on the right of the comma is representing B. So the only possible ordered pairs in this relation where A is less than B is 0, 1, 0, 2, 0, 3, 1, 2, 1, 3, and 2, 3, right? So in other words, the relation is this. So the question you had a minute ago is how many, right? That's, in other words, what's the cardinality of this set, right? The cardinality of the set is 1, 2, 3, 4, 5, 6, okay? Does that answer your question you had a second ago, Isaac? Yeah? All right, questions about that? At least my timing is right. Like when I think I should ask you if there are any questions, my slide comes up asking. We're good. All right. So that's a starting point. We're going to be get some more examples in a few minutes here, okay? But first, let's dive into a function. So what is a function? And this is, I'm talking like mathematical functions, like from your algebra days. What's a function?
Transformation on input data produce output data.
I'll buy that. Okay? Think about it from a computer programming perspective. It's the same idea, right? A function, or in Java we call it a method, right? Object-oriented programming, we call it a method. But it's, you give input and you get output, right? Well, a function is also a relation. Function is a relation. All functions are relations. Not all relations are functions though, right? Okay? It's like when I was a kid and I had a little fort in my backyard and it was boys only, right? No girls allowed, right? Does that mean that all boys belong to that club? No. But it does mean that if you're in that club, you're a boy, right? That was the idea. So all functions are relations, but not all relations are functions, okay? I don't know if that metaphor of the boys club holds up there. I have to think about it. Anyway, it's a specific type of relation. What type is it? It has a couple rules. Number one, every single input has only one output. So what's a function look like from your algebra days? What's a function look like? On a graph.
Y equals X plus 3.
Okay, correct, but give me, like, how do we represent a function? F of X, right? F of X equals Y, right? F of X, you take the value X, you plug it into the function, that will give you the Y coordinate on your graph, right? Okay, it's the same idea. X is the input, Y is the output. Well, some functions, if I put in the number 3 for X, I could get 2 different answers, right? Other functions, I put in 3 for X, and I will only get one specific answer. Okay, if I only will get one specific answer every time I plug in a number, then that's a function. If I get different answers, then it is not a function, okay? So let's start again. Let's let A and B be just some sets with some data in them, non-empty sets, right? And we say that a function f from A to B is an assignment of exactly one element of B to every element of A, okay? I have a set A that has whatever values you want in it, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever. If I plug in any of those values into f of X, the value that comes out of it will be a unique element. It'll be I shouldn't say unique, it'll be the same element for each value of A every time. So if I plug in 1, I'll always get the same B value. If I plug in 2, I'll always get the same B value. And we'll look at pictures in a minute. I know this is a little abstract here, okay? And if I were on the whiteboard drawing this out, it would be a little more clear, but we want to record this, right? All right. So this is how we write it. This is familiar syntax for us, right? F of A is equal to B. If B is the unique element of set B, notice the little b, big B, right? B is the set, little b is an element of the set B, okay? And it's assigned by F to the element little a of A. That's really messy wording there. Take a look at that, make sure that makes some sense to you, okay? F of A equals B, all right? And B is the element that's going to be the result. This is just like your Y, right? F of X equals Y on linear algebra. What's Y? It's whatever the f of X function calculates, right? Well, f of A would be some function that calculates something. It'd be some rule that we're applying to A, and it'll give us the resulting B. All right, that's all that's happening here. And that B will be in the set big B. Okay, and we have names for those. We'll talk about that in a minute. Here's another way we can write this. If it's a function from A to B, we write A arrow B, okay? So that means it's a function from A to B. So basic terminology here. Any questions? Big picture stuff. Okay, we're gonna see in depth. The best way I found to wrap our heads around this stuff is to give you a few vocabulary terms, see if we kind of understand them on a theoretical or high level view, and then look at example after example and just walk through it till we get it. Yeah.
How does that differ from the truth statement arrow? So like where you have
It's just discrete math people using one thing to mean 2 totally different things. Yeah, the arrow, it's not, in the conditional propositional logic, A arrow B means if A, therefore B exists. In this case, we're just saying it's a function from A to B. Yeah, it's just using it in a different kind of way. There's probably a connection there that would make it, you could probably fit it in there, but to me, it's just easy to think about it as just another way to represent it. Yeah.
So is f of A capital A?
I'm like, who is talking? I'm looking around, not seeing anybody's mouth move. Sorry. What's up?
So is f
Say
of
that.
A capital A? Like
No, f of A is little a, right? So look on the last, or the next to the last bullet point. Little a comes from the set cap big A, right? A is the name of the set. So little a is, if the set is A equals the set 1, 2, 3, 4, then little a could be 1, or it could be 2, or it could be 3, or it could be 4. Whatever your domain is, right? Make sense? Yeah. Good. Other questions? That was the weirdest thing, man. I didn't see your mouth moving like a ventriloquist. All right. So next up. So here's a graphical representation of this. One of these is a function. One of them is not. They're both relations, okay? They're both a relation from A to B. One of them is a function from A to B as well. Okay, by looking at that, what do you think? Which one's a function, which one is not? First one's a function, the second one is not. Very good. Why is that?
The second one has, when you put in a function, it can have multiple outputs.
Yeah, so right here, this little guy right here is what breaks it for us, okay? And these are just like purple Twinkies, I guess. If you turn it upside down, it's a Twinkie. The little dots just represent some value, right? It could be whatever's in the set A, okay? But the purple highlights, or the purple circles there are the set, and then the little black dots are the elements in the set. But in this case, the one I've got boxed around in blue there, that is some value that if I plug it into f of A, I'm going to end up with some value one time and some other value a different time. I'll end up with this one time and this another time, okay? That is not a function, that is a relation. We good with that? Okay. You can also represent them on a graph. Believe it or not, I drew all of these in PowerPoint, man. It was a pain. Okay, and so that's why the lines are like, you can see there's a little, kind of a little dent right there in the line, okay? They're not perfect, but I think you get the idea. Which one of those is a function and which one is not? The left one is what? Is a function, and the right one is not. Why is the right one not? Yeah, if I put in a value x, where's my value x where I'm going to have a problem? Take any of them, right? Pick an x spot here, right? If I plug in this value here, I might get this for y, or I might get this for y, right? You know, obviously I can't hone in on the exact point there. You get the idea, right? But like, you know, right, that little point right there, and oh, I did make a little dot there. Or that little point right there, if I plugged in that value, okay? So that's two different possible values for 1x. So if I said f of x equals y, then I could get two different things, right? There's also a little trick we can do. It's called the vertical line test, right? You draw a vertical line through the graph, and if it crosses the actual line more than once, then we do not have a function. In the case on the left, that vertical line, it will only pass 1 point on the graph, not 2 points like we have on the right. Okay, make sense? So questions about that? All right. So a little bit more terminology here to wrap our head around this, and then we'll look at a lot more examples, I promise. Okay? If f is a function from A to B, okay, that's our starting point, then we say that A, the set A, the big capital A, is the domain of f, right? When I have my little f of A equals B, A, that little a, is all the values in big A, which is the domain. That's a term that we're familiar with already, right? All right. Capital B, we call that the codomain of f. It's all possible values that f of A could be. That's the codomain. It is a type of domain, right? It's a limited number of answers, okay? So far, so good? All right. We also say that f maps A to B. That's another term you'll hear. It's a map, okay? And that's a term you'll use if you're a Java person, you've probably dealt with maps. You'll see that in 2420 probably, okay? Dictionaries, right? If you're familiar with that in 2420. So if the function is f of A equals B, then we have the following things, right? We have B, little b, right? Little b. Where does little b come from in this scenario? It comes from the set B, right? Which is the codomain. We say B, little b, is the image of A. Okay, little b is the image of A, which makes sense. I plug in A into my function and I get B. That's the image I get, right? It's A, B is the image of A. Okay? We say A is the pre-image of B. And again, little a, little b. Okay? Which again makes sense. I'm going to plug in this value A, I get the image. Well, little a is like the pre-image. It's what, like before I get my actual image, is sort of the pre-image. Okay? Make sense? All right. Now, look very closely. This is where it's going to get a little tricky. The range of the function, not little a, not little b, but the range of the entire function, or the image of the entire function, is the set of all images of elements of A. So think about this for just a minute. A second ago we said this. I take A, I'm going to plug it into my function right here. A is the pre-image of some value B, right? B is going to be the resulting image of that A. If I take all of those images, all of the B's, right, that are in set big B, that is my range of, range or image of the entire function. If I have in B 100 possible values, will I necessarily use all 100 of them? I won't, not necessarily. If my function only maps to 3 or 4 values in B, then I won't be using every value in B. So B's codomain is everything. B's range is only the stuff that can be mapped to from A. You dig it? Okay, again, we'll look at examples. This is some wordy, tricky stuff here, okay? So questions about that basic idea there? Okay, let's take a look at that one more time. Just look at what's on the screen there for a second. Make sure it's sticking a little bit. I don't expect you guys to be masters of this stuff, but we're going to look at example after example here in a minute. Feeling okay? All right. So let's take a look at some applications here, just kind of where can we see it applied, okay? This is often used in programming to define sequences, which we'll learn about a little bit later, probably on Wednesday. Strings and sequences, there's some very popular sequences that you may have heard of, things like the Fibonacci sequence and things like this. But a sequence is just a set of numbers that is calculated in a specific order based on some formula or whatever, and this can be very useful for this, and we'll see that later. It can be used to represent how long it takes a computer to solve a particular problem of a certain size, which is the entire purpose of 2420, right? We've taken that class, okay? Algorithms are often used to calculate the values of functions, right? So you can just, an algorithm, just a program, just think about a function in code, right? You pass in a value or some values to the function, it does some calculation, and it spits it out. So in this case, it's like a programming function, right? The first 2 bullet points, I'm talking about like a visual way to represent some data to help you think through it. So if you guys have, again, most people have taken 2420, right? If you haven't, it's okay, because you probably will. But you learned about binary trees, or B trees, or left-leaning red-black trees. And how do you use to represent those? You draw, a circle or a square with lines coming off of it and branches, right? That's how you visually represent it. Is that what the computer's doing, though? No, the computer's not doing that at all. You're dumping it into an array, basically, and you write an algorithm that parses through that array a specific way, which treats it like a tree, right? Make sense? Or you maybe did a linked list or whatever, okay? So oftentimes we use the first 2 bullet points to just physically in our own brain to represent the data. That's what's going on there, okay? All right, next thing. We will also write recursive functions. Again, I'm talking computer functions here that are useful tools as well, and sometimes mapping out a mathematical recursive function, which we'll look at later, another day, helps to build your programmatic recursive function. What's a recursive function?
Function that calls itself.
Yeah, it's a function that in the function calls itself, right? It's sort of like a loop, kind of, right? Again, it's a model for representing data, right? It's just another way. A set is a model for representing data, right? A binary tree is a model for representing data using graphs, and I mean graphs from 2420, not the X and Y graphs, but like graphs with nodes and vertices and so forth, is a way to represent data. Okay, this is just another way to do it. And the more tools you have, the more you can visualize the data and make it and turn it into code, right? So here is a visual representation of a relationship. Fake bonus points if you know who those 5 people are. I left out their last names because that might give it away. They're characters in a TV show. Anyone? Yes, Parts and Rec. Nice. Any know the last names for any of them? If you saw any of the episodes with Rob Lowe, you should have the last names memorized because he referred to everybody by the first and last name.
Actually, it's like April.
Ludgate,
Ludgate.
Andy Dwyer, Andy Dwyer, by the way, that's Star-Lord from the Marvel universe. Ron Swanson, Leslie Knope, and Tommy Havelford, something like that. Anyway, let's say they're students though. This is a representation of what grades they're getting, right? Andy's getting an A, and if you know that show, Andy would not get an A. Okay. April getting a C sounds about right. Ron getting a B sounds about right. Leslie also got an A, which is definitely true, and Tommy got an F, which that fits in my opinion. Okay. But what is this? This is a relation from the set of students to the set of grades. Okay. What's the domain here? What's the codomain, and what's the range? So what's the domain? It's a set. What's in the set that we call the domain? You say A. Tell me what you mean by that.
A set of students?
Yeah, it's a set of students, right? So the domain is that. Now, we should put that in curly braces and commas separating it, but I just didn't have space on the screen there. Okay? What's the codomain?
Grades.
Yeah, A through F, right? Same thing. It's curly braces, comma separated. What's the range?
A, B, C, and F.
A, B, C, and F. Very good. Is that you using your ventriloquism again?
Yeah.
You're good at that, right? So, yeah, it's A, B, C, and F. It's all the values that have been reached from A. So, again, the idea is this is the pre-image of that, right? This is the pre-image of that. This is the pre-image of that. So on. That is also the pre-image of that. There's two, so it has 2 pre-images. That's the pre-image of this, okay? And what is what's the range of the entire function? It's all of the images that came from little a. What's little a? Andy, April, Ron, Leslie, and Tommy, okay? All of the images that came from that, which is A, B, C, and F. That's the range, okay? So here's another way to write this out, right? We have some function that's called grades, G. We have G of A equals B. In other words, like G of Andy equals A, the letter A. Make sense? That's just another way to write that mathematically. The top part's a visual representation, the bottom part's a mathematical way to write it. The domain, and this is the proper way to write this, the domain of G is the set of April, Ron, Andy, Leslie, and Tommy. Sorry, I read that out of order. And then the codomain of G is a set of A, B, C, D, F, and then the range, of course, is the set A, B, C, F. Okay, how do we feel about that? I think my next slide's going to ask if you have any questions. Good? See? I feel good about that. That my timing in my brain matches my slides. All right. So how do we represent them, all right? By representing them, I mean, if I need to write them down on a piece of paper, how do I do that? What's the proper way to write down functions on paper? And there's lots of ways. One, we can explicitly write them with the values like you just saw on the previous slide, where we had the picture that with either the drawing, the picture with the actual values, or the sets that had Andy, April, and so forth. That's one way to represent them on a piece of paper, right? Just drawing them out. You can also represent them with a formula, and this is what you should be familiar with, right? F of x equals y. What is y? Well, it's x plus 1, or it's whatever. I think, Isaac, you had a different example, x plus 3 or something like that, right? But it's just whatever the formula. So you could use a formula to represent them. And in some cases, the formula makes sense. Other cases, it doesn't. Like, what would be the formula that you would use to represent G of Andy equals A? I don't know if there's really a formula there, okay? Could be. You could also represent them with a program or an algorithm, right? And that's again, 2420 is all about that, okay? You can also represent them in terms of a relation, and here's what I mean by that. You can say a function a to b is a relation from a to b, right? If you have that function, then a relation from a to b is a subset of the Cartesian product, right? Bless you. And again, the idea here, and this is our fun little notation here, a relation that contains one and only one ordered pair a comma b for every element a that's in the set A, okay? This is messy terminology and it's very wordy, but we're just basically saying that every time I pass in an A, I will always get one specific answer from B. That's all I'm really saying there, okay? From the big set B, right? Every element in A will only have one value in B, okay? And this is just another way to word it. This is how you represent it in terms of relation, right? If I have f of A equals B, where A and B is a unique ordered pair in the relation that has A as the first element, and that little a comes from set A, the big capital A, okay? So again, a function is simple in concept. There's a lot of wordy ways to look at it, but it's a simple idea. Every element, little a, in the set big A, when we plug it into the function f of A, it will result in one and only one specific B value, little b from the set B, okay? Hopefully that made some sense, okay? How do we feel about that? Again, we'll look at more examples here, all right? So let's take a look at a couple exercises, all right? So let's let R be the relation with the following pairs. It's an actor's name and their age. Fake bonus points if you know who those 6 actors represent.
Friends.
Nice. Got a diehard fan over there. Friends, yeah. Okay. So, and those are their ages. I might be off by a year or two because of their birth date hasn't passed yet. It's like, you know, this year they'll turn 55 or whatever, but close enough, okay? All right, so we have this relation that the following pairs are in that relation, okay? In other words, that. This is the relation here, okay? So how did we get the relation? That may be a question, right? What rules did we come up with? Well, let's put the relation that has the birth dates and the ages, or the ages and the person. So here's my question, okay? What would a function to represent this look like? What would that look like? What's the domain, what's the codomain, and what's the range? What would a function to represent this look like? F of name equals age, very good, yeah. Something like that. F of x equals age, where x is an actor, right? And so I pass in x, which is the name, and it'll give me age, okay? That's it, pretty simple. F of x equals age. Now, what calculates that, you know, who knows? If it's a computer function, then maybe we got something that can tie into like the IMD database and pull their birth date down and calculate it, who knows, right? But we pass in a name, and it gives us an age. All right, so what's the domain?
Their names.
Yeah, Jennifer, Courtney, Lisa, Matt, Matthew, David, right? That's the domain. What's the codomain?
Their ages.
There's a tricky one.
Or would you do like a 1 to 100 because it would take care of any ages?
Yeah, so Chad says we could do like the ages 1 to 100 because it would cover every age. Although there are, if I'm not mistaken, an actor or two that's over 100 right now.
What are you talking about? No, live to be like 700.
He's not an actor though.
So I guess you could do 1 to 150.
Yeah, 1 to 150 or the 2, you know, but it doesn't need to be a huge range. What data type would I use to represent that if I were doing this in programming and code? I hear int, which would give us the age, if you're using Java, all the way up to 2.1 billion years old. That's probably a little bit overkill. Short gives us,
To 127, that would probably be okay.
a byte gives us to 127. And if you're using C++, you can make your byte go up to 255 or 56 or whatever. But if you're using Java, it's up to 127. So a byte, maybe a short, just in case somebody's a little bit older than 127. That could happen, I guess. But yeah, so probably, we always use an int though. That's why I asked that question, because I knew that's the answer I would get. We always use an int, don't we? Maybe that's overkill, right? Now with modern computers, memory is not a huge,
bytes.
yeah, it's not a huge deal, but it could become a problem, right? It could be. So just stuff to think about. But yeah, the codomain is some age range, I 1 to 200, I guess, I put a question mark there, okay? What's the range, Jace? Their ages, very good, yeah. The range, and so what would the answer to that be? What's the exact numbers in that set?
50, 52, 53, 55.
Yep, even though we have duplicates, right? Because in a set, we don't care about the duplicates. So 50, 52, 53, 55. The range is only the values that are reached when you calculate all of the values in set A. Okay, any questions about that exercise there? Feel okay about that? So exercise number 2, let's take a look at another example here. This one's a little trickier. It's part of it's like trying to figure out what exactly am I asking you, right? Let f be the function that assigns the last 2 bits of a bit string of length 2 or greater to that string. Yeah, so it's going to take in as an input some string of bits, 1, 0, 0, 0, 1, 1, 1, or whatever, and then the resulting output will be the last 2 bits of that string. So an example would be like that, right? And that should not be IE, that should be EG. Anybody know the difference? That was a typo on my part. IE means in other words. EG is like, here's an example, or example given, right? Here's an example. And so I should have put EG there. Sorry for my bad Latin there. Anyway, okay. But this is an example of what I'm talking about. If I were to pass in 1, 1, 0, 1, 0, it would spit out 1, 0 as a string, okay? So that's the question I'm asking. That's the function that we have that exists somehow. So here are some questions about it, right? What's the domain? What's the codomain? And what's the range? Okay? So what would the domain of this be? Some bit string, right? But let's be a little more specific. Remember, whenever we're talking about domain, look at this very closely, guys. The domain is always what can go here, right? That's the X. The codomain is always this can be, well, this is a little trickier to say this, but the codomain will provide you the possible values that could be for that second box that have 1, 0, right? Yeah, any bit string that's like 2 bits or bigger to infinity, right? It's a big set, so how do you write that out? Not easily, right? We write it like that. That's how I would write that set, okay? Because there's no real way to do that in any other mathematical way that I could think of. What's the codomain? Very good. It's only 4 things. In the codomain is only 4 things, right? It's 0, 0, 1, 0, 0, 1, and 1, 1, right? In whatever order. Why is it only 4 things? Yeah, there's no, if I'm doing binary and I'm looking at only the last 2 digits of whatever string I have, well, there's only so many possible ways you can do that. And there's only 4 different ways we can do that, right? I can have, my last 2 digits can only be 0, 0, or the last 2 digits can only be 0, 1, or 1, 0, or 1, 1, right? What's the range? Well, but remember, the range is made up of every image from all pre-images, right? The pre-images is everything in the domain. So what's everything in the domain? It's an infinite number of strings, right? So if I took an infinite number of strings and I plugged in one by one into my f of x equals whatever, what are the possible images I could get?
Same as the codomain.
Yeah, it's the same as the codomain. I can get every single value of the codomain. So the range is the same in this case. There's a special name for this kind of function we'll talk about in a few minutes. But every single thing in the codomain will be reached if I plugged in my infinite set from my domain. So in that case, all the values will be reached, and therefore my range and my codomain are the same. Okay, third little example here. What is this function saying here? Let's test your symbology knowledge. Set of all integers, right? Yeah, z is for integers, all negative to infinity all the way to positive infinity, right? So let the function be a relation of z, or all integers, on itself, and it's going to assign the square of an integer to that integer. Okay, so what's that function going to look like? What will the function look like? What's the domain? What's the codomain? What's the range? What's the function gonna look like? Remember, it always takes the form of basically f of x equals y, right? So with that in mind, what's, you know, how would it look, right? It's gonna be, what would y look like?
F of x equals x squared.
Yeah, f of x equals x squared, very good. Yep. So we're just saying we have the set z, or integers, and we're gonna plug that into our function, and then the output, our y, will be squaring that number. So what's the domain?
All integers.
Yeah, this guy, right? All integers. So what's the codomain?
Just Z still.
It's still the integers, right? It's still the integers, because it's a set on itself, or a relation on itself, I should say, which means set A is here, set B is here, right? A is the domain, B is the codomain. Now, some of the answers I was hearing in the background for the answer to codomain was actually the answer to what the range is. What is the range? It's positive, it's partly there. It's not quite all integers, though. All perfect squares, right? Okay, what's a perfect square? Any number that has a whole number square root, basically, right? So it's this. Sorry, the Germanic effect wore off there. There we go. 0, 1, 4, 9, right? That's 0 times 0, that's 1 times 1, that's 2 times 2, 3 squared, 4 squared, 5 squared, all the way on up through infinity, right? Why is that the range? Because those are the only possible values that could be reached with that function. Dig it? That's what I'm gonna put on my slides now. Instead of questions, I'm gonna put, can you dig it? Trying to bring back the 70s vocab. Okay, questions about any of that stuff?
So for a function on itself, its codomain is always itself.
So a relation on itself, yeah, the codomain would be itself, yep, yeah. So all relations will be some set A to some set B. Sometimes it just happens that the set you're going to is also the set you started with, and so in that case, that's the domain, and the codomain is the same thing. Yeah, very good. Yep. All right. So here's some examples of where we might see this in the real world. This is, so I've got some Java code for most people in here are Java folks. There's a couple C++ folks in here, and some PHP weirdos like myself, and a JavaScript person like myself as well. I program in all those languages, but not C++ so much, but the other three. So looking at that, where's the domain? Where's the codomain? It's there, believe it or not. It exists. We see this in our real world programming all the time. So what's the codomain and the domain for the Java code there? Good. You guys see that? Okay, so let's think of it this way. Ignore the word int for just a minute. F of x, right there, right? So you're plugging in x. I'm plugging in a real number. So the codomain is all floating point values, and in Java, float is a specific range of floating points, right? And so whatever that set is, which we talked about a couple days ago when we learned about sets in the first place, that all data types are just a set, okay? So the domain is whatever floats are in Java, and the function is called floor_num, or just f, right, for our mathematical thinking. And then what's it return? Well, it returns, according to Java syntax, it will return an integer. So when it returns an integer, it can potentially return any integer, which is in Java negative 2 point something billion to positive 2 point something billion. So that is your domain. Okay. Well, what's your codomain? Sorry, that's your codomain. What's your range is what I meant to ask. And that, I'm just going to assume that you could reach every possible value in the integers. I don't know if you could or not, but you probably could. So we're going to ignore range for now. But do you guys see where the domain and codomain is there, right? How about on C++? It's the same, yeah. Just an extra keyword there, function. Now look at PHP. Any PHP programmers in here? Oh, I thought I saw a hand. I was getting all excited. I got a brother in arms here. PHP. What is the domain? Or JavaScript? Any JavaScript programmers in here? All right, you guys need to take my 1430 and my 2440 class. Okay. Both JavaScript and PHP are what we call untyped or loosely typed languages, meaning you don't have to explicitly declare the data type. In Java, you have to say, this is an int. It will return a float or vice versa or whatever, right? PHP, JavaScript, you don't even have to say whether or not you're returning a value at all. You don't, and if you are returning, you don't have to say what type it is. So with that little bit of knowledge, in JavaScript and PHP, the answer will be the same. What is the domain for each of those? It's literally the entire universe. It's everything. I could pass in an object. I could pass in a string. I could pass in a character. I can pass in a float, an int, a double, whatever I want. I could pass in whatever I want in there. And what is the codomain? Literally everything, right? There's no rules that I could do it, whatever. But it's there. Domain and codomain is in your code. So just think about that when you're writing code, okay? Just plug that into your brain a little bit.